So I want to introduce to you Dr. Connelly. He is from NOC, the UK, who is a member of the Marine Board through NERC and NOC. And he is going to entertain us today with carbon capture and storage and give us a good overview of some of the projects that they've been running. I think we have maybe half an hour or so, and then we'll take the discussion. So welcome everybody, and good luck, Doug.
Good afternoon. Thank you for inviting me to come and do this talk.
Can I interrupt one more time? Sorry. The one thing I was not supposed to forget was to thank the hosts. So I also want to really thank Helmont Centre for hosting us here and for giving us really an amazing area and providing some lovely food.
Thank you, Sheila. So yes, I'm going to talk about basically the assurance integrity of offshore carbon capture and storage. This builds on a lot of projects, but the main projects in terms of what you're going to see today come out of the STEMM-CCS project, which is the Strategist and Environmental Monitoring of Carbon Capture and Storage, which is funded by the EU, finished in 2020. So just as the pandemic landed, we were just finishing. We had our last final meeting up in Bergen literally 2 weeks before Europe closed down. So yes, it was funded on the low carbon energy call. So it was funded through basically DG Energy, which is unusual for a lot of marine work. So what I'm going to talk about, it's refusing to operate.
Try again.
There we go. So what I'm going to talk about is this component, forget the thing, the leakage impact and assurance monitoring. So I'm not going to touch much on capture, storage and transport. That was covered, can be covered by other projects. And it's reasonably well defined, actually. The issue is around, of course, the leakage impact and monitoring, assurance monitoring. It's actually public perception. There's a lot of concerns about if you store CO2 in the environment and basically depleted oil and gas reservoirs or subsea aquifers, if it escapes, can you find that it's escaped? Now, bearing in mind, some of these aquifers are thousands of square kilometers. So the longest running CCS operation on the planet is done by Equinor at Sleipner in the Norwegian sector of the North Sea. It goes into a saline aquifer. Seabed footprint is 14 square kilometers. So trying to monitor and assure basically the regulators that you can detect leakage and quantify it is a prime requisite for any type of rollout of this as a full-scale commercial entity. The IPCC models show that with that, we're going to really struggle to meet the 1.5 degree target without CCS. We're going to need hundreds of gigatons of stored carbon. And the only way you can do that at the moment is, we don't want to change our lifestyles too radically, is to store the CO2 generally offshore. Offshore CCS is a big drive in Europe. There's a lot of public negativity around onshore storage. I'm sure some of you remember CATSIM project in Germany, which people were on the streets and it got cancelled. So offshore is really where it's at. So this is the problem, is basically you've got to detect a small leak in a large seabed. It's challenging, particularly when the baseline conditions aren't known. It really surprised me when we started to do this work. I wanted to get some North Sea data for bottom water temperatures and salinity. It's basically inaccessible. There's a lot there, but it's owned by people that want you to buy it from them. So it's not available. You want to be able to attribute to avoid false positives. There's a lot of natural CO2 in the seawater system. So following a post phytoplankton bloom drops out, gets the degradation, releases a lot of CO2 into the water column. In fact, actually the water column fluctuation in the North Sea is on the order of 1 pH unit naturally over the seasons based on CO2 drawdown from phytoplankton growth and then release when it rots down. So you've got this issue of, can you say that the CO2, if you see a peak of CO2 or a release of CO2 from somewhere in the system, is it natural or is it actually a result of your leaking? This happened in Japan. There's Tomakomai project, which was a pilot project in Japan, got stopped because they've modeled 3 years of so-called baseline data. They had basically a degree of area of how much the pH could change. Second year of operation, the demonstration, the pH went outside that range. The Japanese government stopped the injection, stopped the project. It turned out actually it was a phytoplankton bloom that was more intense than had previously been measured, and it was a CO2 due to phytoplankton. Fortunately, there was a representative bay around the corner, same change in pH was found. So you've got to be careful about that. I'll touch on a little bit later how we might come around that. And it's possible to calculate liquid modelling, but you need to quantify it as well. And quantifying is a separate thing. If you can't model what's going to happen in terms of impact on biology or the wider ecosystem, unless you actually can quantify how much is going to be released. The other side of the coin is the commercial side. If we're asking companies to store CO2, there's generally a tax regime that's implemented to allow that to happen. So the carbon trading system or the Q45 in America or the Norwegian tax system. So stored CO2, you get paid or a tax credit for how many millions of tons you store. The trick is it's got to be stored. So this attribution, if you're looking 30 years from now and we're doing this normally in the North Sea, you've got multiple operators, multiple reservoirs. If there's CO2 found at the surface, whose reservoir is leaking? So that's another thing that's important about the attribution. It's not only that it is leaking, you quantify it, it's where is it? Who is leaking, as it were, into the future? So you can, to find leakage, you can look at precursors. So obviously, as they basically say, we've got a fault, CO2, buoyant CO2 liquid comes up, you get pushed, displaced pore water gets pushed out. It's relatively easy to find pore water. It's rich in sulfides, metals, etc. The formation fluids themselves may come out of the reservoir. And then you can look at CO2 in the water. So basically gas bubbles, easy to find. Or dissolved baits, dissolved carbon species, total alkalinity, carbonate, bicarbonate, pH changes, etc. You've got to be able to target something that will tell you. So with this in mind, we were looking at in our project as to what you would use. Since there's very few CO2 leaks on the planet, and there's none in the North Sea that we can find, lots of methane seeps. There are a few volcanic areas in the Mediterranean, the Panarea site's a classic one, there's lots of CO2. We made our own leak. So basically we wanted to test this. So we built this system. I'm only 20 years old, but I look 70 because of this project. So we had to build from scratch. I thought when we conceived this project, it'd be easy. I'd go to a CO2 company, buy some CO2 as soon as it's on the seabed and release it. No. I wanted to basically drill this well here. So this is my model in the proposal. So we put the CO2 as soon as on the seabed. We drill a directional pipe here, 5 meters down, and then release it below the seabed. It would come out in bubbles, and we'd put all our sensors on the seabed around it. Reality is, you need to buy special pressurized vessels, cost a fortune. Then you've got to put them on the seabed, and then you've got to drill. I could get people to drill me 1,000 meters of pipe in a straight line. Trying to find something that would drill me a curve, and we had to redesign something. So we worked with a company called Cellular Robotics to design a new system for that. We released 650 kilograms in the end. We had 3 tons of CO2 in there, liquid CO2. Released 650 kilograms over 11 days. We slowly upped the rate to try and simulate what a leak might look like. When you get to these 50 litres a minute, I'll show later on, you're at the level of what we think will need to be monitored and detected for offshore CO2 in terms of regulator requirements. So we've tried to make it as real world as possible. We literally threw everything in the box at it. So all of our technologies, we tried everything. Off the shelf stuff, newly developed stuff, things that we could basically say will work or won't work. We wanted fixed point landers, we wanted AUVs, we wanted shipboard systems, and that's what we did. So we did this in the North Sea, and you wouldn't believe this is the North Sea in May. We were absolutely blessed. It was like the Mediterranean. Literally the whole month. It was incredible. Too blue to be the North Sea. This platform, that's the GoldenEye platform. So this is above the GoldenEye Reservoir, which is a proposed storage site operated by Shell as part of the GoldenEye project. This is 13 tons of equipment. That's a gas cylinder plus tracers, etc. This is my drill kit, which was developed by Cellular Robotics. And you can see the drill pipe there. Went down, it drilled, used hydraulics from the ship, put it in nicely, and then we attached this bit here, the box. We ran a pipe to there and joined it into the end of the cable, and then started releasing our CO2. The happiest people in the world, me included, were seeing bubbles break through the surface. It was all reliant. The whole project, 4 years of work, came into place in this. It came to effect in this place. To give you an idea, it was 6.8 tons, 6 tons just for that. This was 13.5 tons. It's the heaviest thing they've ever deployed off this ship. We had some nice, I was told by our outreach people, I want the money shot. I want to see the ship and the platform in the end. So we did some nice drone work. They were happy. We then obviously we threw everything in the box. So we had a series of landers. Then we had AUVs. We were using CFETs off the shelf. We were doing the new lab on chip, nutrient sensors, pH sensors. regular hydrophones, octodes, etc. Put them on the seabed, start the injection. This is what it looked like in our schematic, all nice and clean and tidy. Injection of CO2. We had the CO2 storage reservoir 500 meters away from, no, 150 meters away from where the release was going to be, because we didn't want the tidal effects being, creating a shadow. So that was an issue. This is about should be somewhere like, it's about 7 meters across. That's what it looked like in terms of what it looked like. That's what it looked like in reality. There is light at the bottom of the North Sea. It's 120 meters deep. And this is 7 meters across, and this is some of our systems you will see. So the hydrophone arrays there to pick up bubbles as they come out, chemical sensors. Again, this is pH octodes and a CFET on the ROV. This was a series of in situ pH sensors we pushed into the seabed to see if we could see a plume of the pore water being impacted by the release in CO2. We ramped up over time. So basically we did spend a lot of time recording the background noise because we wanted to see whether you could hear the bubbles. The North Sea is really noisy. And unfortunately, the buzzard platform, 80 kilometers away, they were drilling a new basically pipe, and it was bang, bang, bang. So we were able to do, it was the mother of all devolution in terms of trying to get the signal out. But yeah, so we started looking at the bubbles there. That's how it ramps up over time. We want to obviously maximize the weather, we want to maximize our time on site and test all the releases. I say there's 50 litres a minute. We'll see later on, and it's what we actually expect. So we then looked at how we would measure the flux. So we did different approaches. We did optical. Basically, we had a camera and a light screen, and we just literally filmed the bubbles and then measured the bubbles in terms of analysing the video. We did the ROV, and we collected bubbles as well, and we'll come on to that in a second. We did passive acoustics, so a series of hydrophones, which were laid around the seat, went around the main when, say, the pipe comes on there and the release the CO2 was there. And then basically we reduced position. It was an endless conveyor belt using the ROV of changing systems out every day to make sure that we were getting data back quickly and could analyse it. So yes, it was 50 litres a minute. The seat flow was showing 17 litres a minute from the passive acoustics. So obviously that gives us about 35% of the injected flow is coming out as bubbles by that method. This is what it looks like as well. This is actually the detail. We also added a series of tracers into the gas at very, very low levels. And the tracers are added basically to do the attribution and quantification of the marine environment. So actually, could you use tracers? Because you can use, you can do really onboard, you can do analysis of these things really quickly on board. So this is the system here. So we added these tracers, and you can see the CO2 dissolves really quickly. And over time, by measuring the tracers left in the gas, you can work how much of your CO2 is dissolved, because you know your proportion of tracer into CO2. I say very extremely low concentration of this non-toxic with low solubility. We want to distinguish between that soluble CO2 and that. And some of the models show that you can easily detect CO2 releases from using acoustic like a fish finder, EK60s, because we were finding that most of CO2 dissolved within 6 or 7 meters, and we followed it with the ROV, watching the bubbles dissolve to the point of the detection. So shipboard detection of bubbles is possible, but obviously the issue around those, we don't know what those bubbles are. They could be methane, they could be any other gas. So then we obviously, this is how we actually did the tracers work. We collected the gas samples of the bubbles, which we collected in an inverted funnel into a pressure type vessel, collected on board, and we had the data within about an hour. It was great. So we were able to inform how much we wanted to change the flow rate, etc. So they were very successful. This worked really well. Again, 50 litres a minute. By the guesses, we were getting about between 50 and 80% was dissolving in the pore water, which again is a challenge for how we find these things. Because if it's all dissolving, how do you find using CO2, bubble detection, or even pH changes? So gas bubbles, easily detected on passive acoustics. Optically, if you're right there, you can see them. And then, of course, the tracers also use the gas bubbles, but dissolved, you really need to look at tracers or eddy covariance or benthic chambers. You look at what impact they're having on the environment rather than the actual bubbles themselves. So you can look at the tracers, you see how much is dissolved. Eddy covariance allows you to look at dilution effects, so you can measure your tracer as it dissolves, and you can look at the fact that most of your CO2 is dissolving, and you see where that CO2 is going by tracking your tracers, because you may be so low on the CO2 you won't be able to detect it. So looking at the actual what happened over the experiment, you can see we had natural pH oscillations just due to tidal. Basically, this is just basically a pH change over the day, and basically based on tidal currents. And that's because you're going from deeper water to shallow water in the North Sea, where in, say, 120 meters south, it's 50 meters deep. So you've got a lot of biological process in there. We were in spring. As you can see from the visibility in those underwater pictures, we were pre-bloom, so it was actually had good visibility. When we started the experiment, you can see the big drops of the pH there, and you could see when so if you imagine that you've got the releases here and our sensors are here, and the current's coming from that way, which is what you're seeing here, it's bringing that CO2 change, it's bringing the dissolved CO2 over our sensors. So our lab-on-chip sensors were able to pick up the pH and we were able to calculate the flux. And then we could measure from this eddy curve variance, we could measure how much CO2 was being dissolved during the whole experiment. We had some newly devised optodes, which developed from the University of Graz, Technical University Graz, which are absolutely brilliant. So we put them on the ROV and we run down, go over the plume, and you could see these large pH changes as you went into the plume of dissolved CO2. And you could get higher, you go up in the water column and you could see the signal actually gets quite high, even up in the water column, you can see the dissolved CO2. So there's a lot of promise around these optodes. The nice thing about optodes is they're solid state. There's no reagents or anything. Negative is they get fouled quite easily. So there are pros and cons about all the technologies we looked at. We then looked at everything. So in terms of how efficient the system was, we were finding, so here you can see the current, you can see the pH changes, again, 16 centimeters off the seabed, 87 centimeters off the seabed. This is a comparison of actually the different approaches. So hydrophone measurements, pH and velocity measurements. So again, using the eddy covariant method, directly measuring gas volumes. So we tried to compare all the two. What we found when we compared all the data is 53% of the CO2 is trapped in the sediments. Now, bear in mind, we were only injecting the CO2 about 3 meters below the sediment. So if you do have a release from a deep reservoir, you've got to take that into account. The fact your CO2 might not make it to the surface. That might not be a problem. Obviously, if your regulators are interested in actually when the CO2 reaches the seabed, seawater interface, that's the concern. So yes, that we were seeing that you've got to take that into account, and the fact that most of it will dissolved, and I'd say 47% in the water column, and rose to about between 5 and 7 meters, depending on what the flow rate of the water column was. So in summary of what we actually tried, and say we tried literally everything, detection, most things worked for detection. The reason we took bubble imaging off the detection is you have to get quite close to see a bubble. So it's not really a feasible monitoring technique.
Especially not in the North Sea.
Not in the North Sea. Attribution, only certain things. So we looked at sediment coring. We could actually look at those traces dissolve. We did several carbon isotopes as well. We knew the isotope ratio of the CO2 we were introducing. So we were able to measure that. So you can actually do the core samples. And we were able to measure the CO2 and the isotope ratio, which told us we were actually picking up our introduced CO2 and not the natural one. And then again, benthic chambers, eddy covariance, rate measurements, they all were good for attribution. Quantification, you've got a lot less tools to do quantification. And some of these are such small scale. So you can't put thousands of benthic chambers over the bottom of the North Sea. So you probably tick that off in terms of a measurement technique, in terms of a regulatory technique. We had a lot of debate about this. What's acceptable leakage rate? What will the regulators want to see? What will the public be happy with? Onshore, basically they look at 0.01% reservoir loss per year as being the regulatory limit. And therefore applying that for an injection of 1 million tons a year for GoldenEye. GoldenEye is just a demonstration project, just 1 million tons a year. Basically, you're looking at 247 kilograms per day released. So our release rate was similar to that, and 5,000 kilograms over 20 years. Now, that's only 1 million tons a year. That's what Sleipner does. So the Sleipner reservoir, that's what the Norwegians have been doing, Equinor have been doing for about the last 25 years. So we know that's feasible. If you scale up to 100 gigatons, then you've got to start thinking about what you actually are going to be acceptable levels of release. And then we had leakage of 67 kilograms per day of the amount that we injected. So again, roughly over half of it being released. And you can measure it in all its forms, gaseous, dissolved, in both water column and sediment. So you probably could look at a 0.01%. We've got the technology to measure that. So the regulators should have some faith that we can actually, we've got the technology, if not now, in the very near future to be able to do that. So when they're forming the regulations, if they just want to mirror what we're doing on shore, it's sort of doable. So So yeah, we did. In conclusion, we did this detection, tried everything. Even at very low rate, we could find the CO2. It's dissolved. Again, we tried everything existing and techniques, different techniques. One of the big questions we had. So one of the ways that they monitor onshore storage, they use drones and they measure nitrogen, oxygen, CO2, and they measure the proportion of CO2 to oxygen, and they use basic stoichiometry. So if the CO2 changes but your nitrogen doesn't, it's a CO2 source. If your nitrogen and CO2 changes, probably degradation of organic matter. Same in the ocean, but of course you can't measure nitrogen in the ocean. So our lab-on-chip sensors, you saw in that suite, we had Newton nitrate, phosphate, silicate. The idea was that we could actually look at those relative to CO2, and they worked far better than we actually dreamed of. You could actually see the natural background when the current was going the other way and we were getting no input from the actual release CO2. You could see the natural degradation of organic matter in nutrients and pH and O2. Then when it turned the other way around, it just got swamped by the CO2 signal. So that was really reassuring. In fact, actually, we've just taken on the person who did that as a staff member at NOC because we want to explore that a lot more. So you could, basically, you should implement, you can use them for MMV. They're working on a project Green Sands, which is a Danish project with the Danish government. They're going to inject next week, start their injection for Danish CO2. It's partly in a project involving ENEOS, hydrocarbon, and they're going to be doing that, and we're applying our MMV technology for that. The developments that we're doing in this project are being used for that. So I'm going to show you a nice little video, which we did at the end of the project. It should work.
Following 3 years of careful planning, preparation and technical development, an international team of scientists and engineers departed Southampton at the end of May aboard the RRS James Cook on a research expedition to the North Sea. Led by the National Oceanography Centre, the aim was to test sensors designed to detect escaping carbon dioxide in the unlikely event of a leak from a sub-seabed storage site. The site chosen for this experiment was close to Shell's GoldenEye platform, 100 kilometres off Scotland's east coast. Here, the team rendezvoused with project partners from the German research organisation Geomar aboard the research vessel Poseidon. The first stage was to use a specially commissioned drill rig built by Cellular Robotics, lowered 120 metres to the seabed, to push a curved pipe into the sediment with its outlet 3 metres below the seabed surface. Next, the bespoke carbon dioxide and trace gas cylinders in their cradle were lowered over the side in a very delicate operation. They contained 3 tons of gas, which was to be pumped through the seabed pipe over 11 days, to test whether an array of sensors could detect the deliberate release within the sediment, at the seabed surface, and in the water column above. The cylinders were connected via hoses to the inlet on the pipe, using a work-class ISIS remotely operated vehicle, demonstrating the skill of the ROV pilots. Sensors were positioned around the area where the gas was expected to bubble through the seabed. These included optodes, acoustic detectors and a range of other platforms carrying sensors to detect the chemical signature of the carbon dioxide and the traces that gave it a distinct chemical fingerprint. The gas was turned on, and to a collective sense of relief and jubilation, the gas began to emerge through the sediment. Quite an achievement. More sensors were positioned to sample the gas, and even to film the bubble stream, with an optical array to capture how the gas behaves as it leaves the seabed. Gas samples were collected for later analysis, as it left the sediment, and within the water column. The local residents, an eel, an octopus and a Norway lobster seemed more curious than concerned. Nearby, sediment cores were also taken for further investigation into how carbon dioxide reacts within the sand and mud. Back at the surface, a Gavia autonomous underwater vehicle armed with sensors was launched to take further readings in the vicinity of the release site. With the work completed and declared a great success, the ROV dived again to uncouple the gas supplies and retrieve the equipment from the seabed. The Strategies for Environmental Monitoring of Marine Carbon Capture and Storage (STEMM-CCS) experiment has shown for the first time in a real open water situation at depth that we now have the sensors that can detect even small releases of carbon dioxide. This should increase confidence that if a leak occurs, however unlikely, We now have the technology to find it and monitor its progress and effects.
That's sort of a nice little 2-minute summary, which we sort of did at the end of the project. It really was a great success. We were, big. There were big size relief. We got some resources online, so we had a special publication. So a lot of there's a highlight paper that I led on, which is just typical sort of little bits of snippets of information, but no real detail. There's 28 papers in this special edition of the International Journal of Greenhouse Gas Control that covers every component of how we looked at it. There's a bit of the project I didn't talk about. We also had a geology-focused project, which was looking at existing geological features in the North Sea. So the chimneys, the so-called old chimneys, and to whether they could actually act as a conduit, because some of them go quite deep. You can imagine if you're using a reservoir at 2,000 meters, if one of these chimneys actually intersects it, what happens? Is there, because we don't know how the chimneys are formed. We assume that they are formed from basically calcium carbonate precipitation due to methane leakage over the millennia. And so calcium carbonate is nicely soluble in CO2. So the idea was, well, if they insect it and you're introducing CO2 into the depleted oil and gas reservoir, would it start dissolving? So we did a lot of work on that, which was, we drilled for the first time ever one of these chimneys right down the middle, which was great. We've got a geology project. We compared and contrasted that with some onshore analogues in California. And they are calcium carbonate, and we're still doing the aging and everything on that. And that ties to a project we're doing with the Norwegians up on the Vassnisa Ridge again. So the project was a great success. The project has a legacy. We are talking to the NSTA, which is the UK regulator for offshore monitoring. We're part of the project, as I say, the Project Green Sands. We're also part of the advisory committee for a number of these projects around the world around rolling out regulation. There is no existing regulation yet in terms of what people need to monitor. So the NSTA and the Americans are particularly interested as to what can be measured and how it would be measured in the real world. As I say, you've got to monitor very large areas of the seabed. Even on the Golden Eye, which is an old oil and gas reservoir, it's 120 square kilometers. There's pros and cons. There are big benefits to using depleted oil and gas reservoirs. You've often got the infrastructure there. You've got pipes out there. You can send the CO2 and it can be injected. The oil companies know exactly where the oil and gas was. So they know the 3D structure of the reservoir, but they've got a finite volume. Whereas if we're going to literally store hundreds of gigatons of CO2, we're going to need to use aquifers. Aquifers are a little bit different. They large open reservoirs normally. Sometimes the outcrop, there's an endurance reservoir in the North Sea, sits in the central North Sea, about 60 kilometers south. The hypersaline formation fluid outcrops on the seabed. If you start putting CO2 in, what's going to happen? Are you going to increase the hypersaline release? Mm-hmm. So formation fluids can be as equally dangerous. Hypersaline fluids are quite deleterious to some marine life. So in terms of the impact on marine life, we had another project called ECO2. And at the constant, what we found in ECO2 was that release of CO2 into the marine system, particularly the North Sea, shallow environments where it's very active, physically active, we couldn't see big signals or big impacts of CO2. Even when we did artificial releases and then modeled it, it wouldn't impact most biological life. And as you can see, the biology swam away or can swim away if it gets negatively impacted. In terms of the comment about the baseline in the North Sea and all oceans is changing as well. So any regulation you come up with has got to take account the fact that we are making the oceans more acidic due to continued release of CO2. But I will give you an old axiom that the company, Shell were a partner on this, and Shell say, at the moment, we're releasing all the CO2 we produce. So CCS isn't a solution, it's a stopgap. Give us time to transition into low or no carbon emissions. It might give us that bit of time. As I say, all the IPCC models show that we will need to use CCS to meet the 1.5 degree target. I'd like to thank you for your attention and
I think